Lecture 1.12 is about molecules motions and elements motion, molecular speeds, and how it relates to temperature and how temperature relates to overall energy. And then eventually how we measure total energy. Any case, what I have here is an animation from Norton.com, and there's plenty of nice tutorials there. But if you notice, I have something up for a molecular speed, and we should know that temperature is the average kinetic energy, but we're going to use this speed or this translational motion as part of our discussion today. So in any case, let me go back here. No, I'm going to go here. What I have to the right is a Boltzmann distribution graph, and I have some gas molecules at 200 Kelvin. We should understand what that scale means. It's below freezing. And notice the motion. And again, the motion of these molecules is random, and some are going near the mean or at the mean, and some are above, and some are below. And what you should know is that as we get pretty cold, this line extends up because we have a limit. That limit is 0. Now, if I was to speed this up, add 1,000 more kelvins to the gas molecules, you notice the graph moves out. Molecules are now moving faster. They have more energy, and temperature is just measuring that average. Some are below and some are above. Don't worry about this. You are root mean squared. It's something we can talk about in AP. And then if I add another 1,000 more kelvins, notice my graph is again being flattened out, and the speed has increased. The area under the curve is constant. The number of molecules we're talking about is constant, but as we get colder, it moves out. So this was the reason why I showed you Boltzmann distribution graphs, was the idea that you can understand that temperature is just an average. This line represents the average, but we have some below and above. So that's why temperature is not a direct measurement of energy. Yes, it gives us a range of motions, an average, but that average is what we use to get the total energy. Now this diagram I revisit, we did this in class to show you that what we're measuring in temperature is the average of these motions, okay? So this type of vibrational motion, there's 3 types. There's translational, moving left to right or up and down. There's rotational, and now we have this vibrational, and these are the basic vibrational motions. I want you to get the idea that temperature is really a measure of this vibrational energy, and of course it is an average. We often talk about Christmas in July, molecules as a okay, sorry again, didn't have that movie loaded. In any case, we took a temperature as the average kinetic energy, the average motion, and I played this for you in class today to show you that gases clearly or molecules move at different speeds, some faster than others, some slower, and that's why there's a range. Okay, and that's that motion I talked about. Now I'm showing you translational motion, but really it's the vibrational motion that temperature represents. This translational movement, moving left to right here, is really what gives the appearance of gas pressure. But in any case, you can see as you get warmer, that graph gets spread down a little bit. Okay, and that's all I wanted to show there. Okay, and of course, this movie here was a way to show that cars on a highway move at different speeds. If you took the average speed, you would get this graph.
Cars on highways travel at a variety of speeds. To show distribution of automobiles.
There's only 1 star in this movie, and I'm going to speak. So in any case, you can see that the faster cars clearly represent this area. The middle cars here, and the faster cars up at this end. The slower cars at that end. All right, and that's why this there's a range of temperatures. I think I beat that to a brown pulp. Let's move on. Okay, I didn't get to play these 2 movies about heat flow, but let's play this one, and I'll add. Let's see if you can hear what this person has to say.
Molecules of a hot substance move more rapidly than those of the same substance with a lower temperature. If the 2 samples come in contact, a transfer of molecular momentum occurs from the rapidly moving molecules to the slower ones. In this way, thermal energy transfers from the hotter sample to the cooler one. When the two samples have similar rates of molecular motion, they have reached thermal equilibrium and have the same temperature.
So yes, there was a student in class today who talked about the flow of heat from hot to cold is to achieve equilibrium. I believe that was Laura. Good job. And that's one of the driving forces in nature to go toward equilibrium. But also my analogy of the lab coat techs who are counting blades of grass in Central Park getting run over by a rugby team. Same idea. Transfer of thermal energy from hot to cold, because in fact the warm molecules have the ability to get to the cold molecules. All right, and they'll play this one. I'll share some of the wealth also with this lady.
Gas molecules are in constant motion and frequently collide with one another. Although not all the molecules in a gas sample move at the same speed, the higher the temperature of the gas, the greater the average speed and kinetic energy of the molecules overall. This higher level of energy allows molecules to disperse more readily, which is one reason we smell aromas better when temperatures are higher.
So again, very simply, higher temperatures, higher average motion. But again, temperature alone does not measure total energy. As I said in class, if I look at the computer you're looking at tonight, and I said, what's the energy of that computer? Very difficult type of quantitative value you can try to get. You can't really come up with a value of that computer, but you could try to talk about the type of energy that flows into and out of that computer as its temperature changes. And that's what we do. We evaluate energy. We're talking about how much change of energy really is occurring in and out of a substance, and that's where calorimetry is born. Before I get to calorimetry, we're going to talk about what we do when we're looking for total energy. So temperature tells us, gives us a sneak peek in types of the average motion. It certainly does tell us that if the average motions were to change, obviously if the average motions increase, temperature is going into the system. If the average temperatures decrease, energy is going out. So temperature change is very important. Temperature alone doesn't help us. It's the change in the average motion that gives us the amount of energy that goes into or out of a system. So our basic thermal equation has to be built upon energy equals the average times how much. I gave the analogy in class. If we wanted total points of all students using GPA, I would take the class average and times it by the number of students. So if I've got 10 students and the average is an 80, 80 times 10 is 800 points. All right, and that would give me a total value. A class average of 80 with a class of 2 would give me 160 points. Even though they have the same class average, the one with the greater number of matter, of course, would have greater amount of energy going into or out of. So this is the first step. How much of matter we have times a change in average motion gives us the energy. We're making a huge assumption here. The assumption that we're making is that the compounds themselves all change temperature evenly. And we're going to find out during the year why that isn't the case. So we need something called specific heat. Specific heat factor takes into account that some compounds do not conduct electricity very well or do. It really measures its ability. All right, now what is the definition of specific heat? Well, it's the amount of energy it takes to raise a gram of a substance 1 degree Celsius or Kelvin. Okay, and case in point, if I have 100 joules of energy going into, let's say, a piece of metal or a piece of wood, okay, the temperature change of the metal, let's make the top one the metal, is 10 degrees. Whereas the same energy that goes into a piece of wood, which we know is a terrible conductor, that's why it's an insulator, is 1 degree Celsius. So everything being the same gram, same energy, it's clear that there's a factor of a 10 difference between specific heats. Okay? So a large change in temperature must mean a smaller, okay, specific heat capacity, which means it takes less energy, okay, I'm sorry, it takes, it takes less energy, 10 joules, to move it 10 degrees with the same amount of energy. Or you can think of it this way, with the same amount of energy, it takes, there's a lot more change in temperature for the same energy. Its specific heat has to be smaller. Some people think of specific heat as energy cost. If you think with me for a second, the cost of heat conductance. So if I have a compound that wants to have some heat traveling through it, you're going to lose some. We always lose some. What's that amount we lose is the specific heat when you think about it. If I lose a little bit, notice this low specific heat, okay? That means most of it gets conducted and the change of temperature is high. If I have a lot of heat that does not get conducted through the material, okay, I have a high specific heat or a high cost. There's a tremendous cost, which means heat that's trying to travel through a substance, okay, doesn't get to the other side because of other reasons we'll talk about. So therefore, there's a higher specific heat. It's a higher cost, meaning if I'm trying to give 100 joules to something, 100 joules doesn't get to the other side, so to speak, okay? And I gave you a list to look at, okay? And you notice metals have low specific heats. Water has a very high specific heat. And in class, I was talking about how water takes a long time for water to heat up and also cool down. And that's why we use it to radiate heat in our houses, okay? And of course, it's the reason why the island is very temperate climate, because very simply, it takes a while for the water to get cold, which keeps our winters warm, and it takes a while for our water to warm up, which keeps our summers cool, okay, relatively. All right, so that's a very important concept, molar heat capacity, okay? And looking at the units, it's very important you understand that. So looking at our units and our thermal equation of heat equals mass C change in T, if we solve for C, you're going to get heat over mass and change in temperature. Okay? And generally speaking, if we have joules, that goes there as your heat, mass is in grams, and change in temperature could be degrees Celsius. Okay? And if it's in calories, we use calorie over grams degrees Celsius. Now you could use degree Kelvin, or kelvins I should say, no degrees for kelvins, interchangeably, because a Kelvin and a Celsius are the same size, so a change in that temperature doesn't matter. Of course, this is 4.18 joules, and this is 1 calorie. This is given to you in table B of the reference table. And this one's the easiest number to remember. Remember, calorie by definition is the amount of energy it takes to raise 1 gram of water 1 degree Celsius. So something with a higher specific heat needs more energy to change it 1 degree per each gram. This is a lower specific heat. Oh, I'm sorry, I can't compare joules to calories. These are the same amounts for different units. Okay, so when you compare specific heats, that's what we do there. So that's the units. Okay, now also something else you should understand before I finish this discussion is this is always the same stuff. So this is going to be water. We use water mostly, as I alluded to in class, because we use something called calorimetry. Calorimetry is the idea that we take, oops, let's undo that. Or I just moved down, I guess. So it's the idea that I take a container, usually a sealed container, and I have its water, and I have a reaction, okay, or a reaction of some sort in the container. All right, and let's say it's an exothermic reaction, and energy is released. Well, if it's an exothermic reaction, a chemical change occurred. That means I no longer have my original substance I was testing, which means I don't have its mass. I certainly don't have a temperature change for the substance. Its specific heat is something I could find. But what do I have? I have the surroundings, the environment. And this is an important concept. Surroundings is going to be the water. We're going to use the water as the environment. So we can't directly get the Q of, let's say, a Cheeto curl. Let's say a Cheeto. I'm going to find the energy of a Cheeto. I can have its mass of the Cheeto. I can have the specific heat, but change in temperature is very difficult because it's no longer a Cheeto. Once I burn it, it becomes a carbon carcass. So very difficult to do this. But here's what we can say is the energy released by the Cheeto equals what? The energy absorbed by the water. So Q of the water equals Q of the Cheeto. We can't do the Cheeto directly, but we know that the energy absorbed equals the energy released. because of conservation of mass. Now we're assuming this is a sealed container and the only heat flow is between the reaction and its environment, which is the water. Okay, so if these are equal, I don't have to consider the Cheeto. All I have to do is the Q of the water. And that's why you'll see a lot of these questions with water. Hey, what's the energy of the water that was needed to raise 100 grams of it? Okay, 10 degrees Celsius. And of course, if I'm looking for joules, I need a specific heat that's in joules, and the unit is 4.18 joules per gram per degree Celsius. That tells me that these have to be grams, so grams cancel, and Celsius, Celsius.